All right, so this is the first video. We're gonna go through SN1, SN2, E1, E2. Um, yeah, screen share. All right, this is the first video. We're gonna go through SN1, SN2, E1, E2. All right, so substitution and elimination reactions of alkyl halides. Alkyl halides, first of all, are anything of the form RX, where X is a halogen. The modes of reactivity for Cl, Br, and I are generally the same. F is a little bit different, but we'll get to that. So the characteristic thing about alkyl halides is this is a polar covalent bond, right? So we're effectively pulling electron density to this halogen group, and we're creating a pretty good electrophilic site right here, right? So just to give the general structures, this is the substitution reaction. It forms two products. An elimination reaction, it's actually pretty important to note that it forms three products. And we'll get to why that's important later and with how we go about favoring elimination versus substitution, etc. All right, first off, the SN2 reaction. So this S stands for substitution and nucleophilic 2 bimolecular, which means that the rate determining step is where two molecules are reacting with each other, right? It's a concerted mechanism. Um, so let's take a look at the mechanism. The mechanism is backside attack, right? So we have a Br, which functions as our good leaving group. We have a strong nucleophile. We attack here. We kick off this Br. Awesome. So it's important to note that both the nucleophile and the alkyl halide are involved in the rate determining step. The nucleophile must also approach the alkyl halide opposite to the leaving group, right? So this is a backside attack, and that's just because it is stereo. The three orientation of it favors this because there's just, if we try to attack from this side, there'd just be more stuff in the way. So stereochemistry is inverted. A quick note on the inversions here. Generally, like you'll see that a wedge gets translated to a dash gets translated to a wedge. Um, Sometimes you'll have a problem, like for example, like in epoxide, where the lines are not wedges or dashes. And in that case, it might not be readily obvious what to install or where to install. Right, because if it was just a wedge or dash, we'd know to like put the opposite of it. And in that case, up in the plane is opposite to down in the plane. And we'll see examples of that later on. All right, evidence for the SN2 reaction. These are just like some of the experimental things they did and some things they realized. The rate of the reaction is dependent on both the concentration of the reactants, so the nucleophile and the alkyl halide. Steric hindrance becomes really important throughout this course, specifically in substitution reactions. So the bulkier the substituent, the more volume they will occupy, thus slower reactions. So if we look at reaction rates, we'll see that this will be faster than this, will be faster than this. This doesn't really happen. You never, ever, ever do an SN2 reaction on an alkyl tertiary halide. No reaction, okay? So moving steric bulk away from the reactive site will also affect the rate of reaction. This is something called beta branching, and obviously the position we attack is here. And while the steric hindrance isn't directly on that spot, it's still occupying space in a 3D orientation, right? So while it's not directly in the spot we're attacking, it still is not great, right? And with that, like, you know, it doesn't prevent reactions, but it does slow them down. Okay, asymmetric center. Okay, cool. Okay, factors that affect SN2 reactions. So leaving group stability is the major one. If we see here, I, if you looked at a periodic table, is significantly larger than Br, significantly larger than Cl, significantly larger than F, right? Cl, Br, and I all have the same modes of reactivity. F is a little bit different. Generally speaking, the weaker the base, the better it'll act as a leaving group because there's a more stable negative, right? So since I is so big, once it leaves, we can spread it out over a really big area, right? And, we define the stability of a weak base by also the strength of the conjugate acid, right? And vice versa. And we know that the bigger the group is that's stabilizing the negative charge, the better it's going to be. So we do not use fluorine as a leaving group. Fluorine is a really bad leaving group. And we'll see an example of where it goes anti-Markovnikov, or sorry, not anti-Markovnikov, but it'll not leave in the way that you think it would. Okay. The nucleophile, basicity, how well a compound shares electrons with a proton. Nucleophilicity is just how readily a compound, a nucleophile will attack an electron deficient atom. A better nucleophile will just have a faster SN2 reaction. So the major things that affect nucleophilicity are basicity and sterics, okay? A good nucleophile has a minus charge, right? When we have a minus charge, that means we have electrons located in one position, very local to one area, which means we have a really good way to attack. So SN2 will generally happen if possible, and SN1 will also happen if there's other considerations. A poor nucleophile will always be neutral, and it'll only have SN1 reactions. So if you see a neutral nucleophile, you immediately know it's either SN1 or E1. And generally speaking, if you see a good nucleophile, you can expect it to be SN2 and SN1, or SN2 and sometimes SN1, but generally SN2 and E2. And we'll get to eliminations in a second. Okay, basicity. If attacking atoms have the same size in the same period or the same atom, the stronger base is the better nucleophile. Okay, stronger base. This is just ARIO, the mnemonic that we learned back in 109A. If atoms have different sizes, we're comparing down a group. So we consider the polarizability of the atom. All this is saying is, that when we're comparing down, we care more about the size, right? Because 16 is much bigger than, like much smaller than 32, right? Double the size, right? So it really makes a difference versus 14 to 16, like, 16 is bigger, but it's not dramatically bigger, right? That's why we care more about another effect. We care more about electronegativity. All right. Okay, the solvent chosen will also affect the nucleophilicity of a nucleophile. So the solvent resolves competing benefits of polarizability and basicity in atoms of different sizes. So generally speaking, there's two types of solvents, right? There's polar protic solvents and polar aprotic. Polar protic just means that they can be hydrogen bond donors. So there's an H attached to the O or the N in the solvent, right? So alcohols are polar protic. Water is polar protic. Carboxylic acids are polar protic, right? Versus polar aprotic just means they do not contain a proton or specifically on the O or N, and they're not a hydrogen bond donor. All right. So the more a nucleophile interacts with the solvent, the worse it's like the less it's going to be, the worse of a nucleophile it's going to be. So protic solvents can hydrogen bond with anions, which helps stabilize them and makes the nucleophile less available to act as a nucleophile, right? Because when we have all these different interactions, we're spreading out this electron density. It's no longer localized to a specific area, which makes it really hard, right? Because the more negative I have in a small area, the easier it is to be able to attack a positive. In polar aprotic solvents, strong bases mean strong good nucleophiles. In polar aprotic, strong bases, good nucleophiles. Protic, strong bases, poor nucleophiles. Okay. If attacking nucleophiles different size, you consider the solvent. If attacking nucleophiles are similar in size, ignore the solvent. Stronger base, better nucleophile. When we talk about ignoring the solvent. Okay, sterics. Sterics are so important and they also play a role in all of this. So the bulkiness of the nucleophile can affect its nucleophilicity. Terbutoxide is a stronger base than ethoxide. Ethoxide is a better nucleophile than this. So when we talk about sterics, a lot of times it'll be considerations of are we using elimination or substitution? And we haven't gotten to elimination yet, but when we get to that, we'll discuss it. Okay, so overall, when considering a better nucleophile, negative versus neutral, the strength of a nucleophile is a base, size of an atom, solvent, bulkiness of a nucleophile. All right, SN1 reaction, the solvolysis reaction. So this is just called the solvolysis reaction because the solvent is the thing that's acting as a nucleophile, right? So H2O is both the solvent that this reaction is going through in, and it's also the nucleophile, the thing that attacks the alkyl bromide, right? And we see here this is tertiary, which means that we're not going to have SN2 because we have both a poor nucleophile and we have a tertiary alkyl halide. And we also know that tertiary alkyl halides can never go through SN2 mechanisms, irrespective of what we have. So the nucleophile is the solvent in SN1 reactions. Unlike SN2, where solvents and nucleophiles are separate, right? When we looked at SN2 reactions, this is not the solvent. OH minus is not the solvent, right? Okay, well, so this is the mechanism for SN1. We go through a carbocation mechanism, and we should note that whenever we go through a carbocation mechanism, it's privy to all of the things that we learned about in 109A, whether that be rearrangements, whether that be racemization, whether that be ring expansions, ring contractions. So just keep that in mind. Be wary of when we go through a carbocation rearrangement, there's a lot of things that can happen. Okay. This is all okay. Okay. Primary and secondary alkyl halides don't undergo SN1. The caveat to that is benzylic and allylic resonance is often the caveat to a lot of things that wouldn't really happen without it, right? We learned later on in chapters 16, 15, 17 about how um, resonance really helps out with reactions. All right. Okay. So overall, this is the difference between SN1 and SN2. You could pause the video here at this point. I'm not going to go through every single one of them, but it's really important to have a very good understanding of this because it's really not going away. Whether that be for the rest of 109B or OSU 109C or biochemistry when you take it later on. Okay. So these are some examples. Also, pause here, go through it on your own, and make sure you really understand what's going on here, why we're getting the types of reactions we're getting. SN1, weak nucleophile, SN2, strong nucleophile, SN2, strong nucleophile, not tertiary, SN1, primary, no reaction because we don't have a strong nucleophile, and we don't have a stable carbocation position. Okay. Benzylic, allylic, and vanillic halides. So these behave a little bit differently than the ones that we just talked about. So first of all, primary and secondary benzylic plus allylic halides will go through an SN2 reaction. Tertiary benzylic and allylic halides will not go through an SN2 reaction. So very important to note that even though we have resonance for tertiary benzylic and allylic halides, there's just too much sterics. Okay. And again, like I was talking about here, we have resonance. In this case, it doesn't really matter because these are the same molecules, but you could plausibly see how this might not always be the case, especially if we had a longer carbon chain. Vanillic and aryl halides. So vanillic is when we're specifically attaching a Br to one of the double bonding carbons, as opposed to being one carbon spaced out from a double bond in alkyl halide, right? This is called a methylene linker if you want to get funky. These don't undergo substitution reactions. SN2 reactions are blocked by the pi electron clouds. SN1 reactions form too stable of an carbocation. These never go through stuff, right? So when you talk about which one is more likely to undergo a reaction, it'll be the benzylic one because this does not go through an SN1 reaction or SN2. Okay, William Etherson synthesis. So NaH is really popular for alcohol deprotonation. I can almost guarantee you whenever you see NaH, it'll always be in the context of deprotonating an alcohol. So we can talk about how we synthesize ethers, right? So the idea is that we have this compound and it can be broken up into either this or this. So we have one alcohol and one alkyl bromide. For this, both methods are viable because we have primary alkyl halides. However, this isn't always the case. So if we had this compound and this compound, the red reagents would be the ones we choose and not the blue. Because remember, this proceeds through an SN2 mechanism, right? We have a backside attack, we kick off a leaving group, which means that we wouldn't be able to have a backside attack on a tertiary alkyl halide, right? Especially this is a really bad, nucleophile too. You could be like, oh, maybe it's SN1, but it's just, not exactly the case. And there's some more considerations there, but generally speaking, for the purpose of Williamson ether synthesis, it doesn't matter which alkyl halides you use if we're primary, but if we're tertiary, make sure that the tertiary group is connected to the alcohol. Okay. Williamson ether synthesis is also used very frequently when you want to make 5 or 6 membered rings. You cannot ever make 3 or 4 membered rings within Williamson ether synthesis. You use other reagents to make 3 membered rings with oxygen. We'll get to that later, but again, NaH will deprotonate the alcohol. We'll attack here. We'll kick off the Br. It's exactly like this, where we have one reagent attacking another. It just so happens that the 2 functional groups that are involved in this reaction are connected on the same molecule, right? So this is pretty easy to predict. 1, 2, 3, 4, 5, 6, 6-membered ring. 1, 2, 3, 4, 5 carbons, 1 oxygen. 1, 2, 3, 4, 5 carbons, 1 oxygen, right? So, sometimes it's a little bit hard to redraw, but, always make sure to count your carbons and go slowly through these steps because it's very easy to make mistakes. Okay, the E2 reaction. So there's 2 types of elimination reactions, E1, E2, and we're going to talk about E2 first. So E2 is a bimolecular elimination reaction, which just means that there's two compounds involved in RDS. This is the overall transformation. It forms three products. And the more beta hydrogens we have, the higher reactivity, right? The more spots that we can attack to form a double bond, the better off we're going to be, right? That makes sense. So this is the overall mechanism. We have a strong base for E2 specifically. We pull a hydrogen. Those electrons in the bond go down here, and then we kick off the BR. So this is a concerted mechanism, so we don't have to worry about carbocation rearrangements. E2 reactions are also regioselective, which means we'll form more of one constitutional isomer over the other. We're going to form the one that has a more stable alkene, right? And this is Markovnikov's rule, and it's also a result of the transition state stability. So we'll see that when we form the more stable compound, we just have a much more stable transition state, right? Because if we look at these two diagrams, this one has a greater stability than this one. Okay, cool. The most stable alkene is not always going to be the most substituted alkene. So this is an example of a conjugated diene. We have resonance conjugation because we have two bonds, one apart. Isolated diene, we don't have this conjugation. Even though this is a tertiary and secondary position, this is secondary, but it's secondary allylic, which beats tertiary. Generally speaking, allylic positions and benzoic positions will always beat the higher substituted thing. Okay. If the alkyl halide is bulky, then the base is also going to be bulky. And the base is bulky, the major product is less stable, which means it's easier for a base to pick up a hydrogen. Bulky bases and bulky alkyl halides generally result in a less stable alkene. So this is not bulky, no worries. These are both bulky. Major product is this. It's less stable. And, like the reason why we form this is because it's just hard to make this compound, like sterically speaking. Like this molecule can't get to this area, right? It's easier to just grab something from here, go down, kick this off, right? Okay. The two bulky bases you're probably used to. I don't know if you've seen DBU, but tert butoxide is a fan favorite. Okay, alkyl fluorides. So this is what we talked about earlier. Alkyl fluorides react a little bit differently than the rest of the halogens. Alkyl fluorides will form the less stable alkene, and that's because they're really, really bad leaving groups. So they don't immediately leave. They're effectively going through like a quasi carbanion state, and we know that carbanions actually prefer to be on the less substituted position, right? Because hyperconjugation says that we donate electrons to the corresponding carbons adjacent to us. And if we already have extra electron density, we don't want even more electron density, right? We want as little as possible because we have a surplus. Okay. The E1 reaction. So this one is an elimination unimolecular. This is the general mechanism for it. Okay, this one is highly regioselective. It'll almost always form the most stable alkene. Relative rates of leaving group are exactly what you would expect. Elimination 1 only works with tertiary alkyl halides and stabilized carbocations. So we can have a tertiary alkyl, we can have a primary, secondary, tertiary, allylic, or benzoic. Again, resonance is always the exception. No E1 there's no E1 on primary or secondary alkyl halides that are not stabilized by resonance. An allylic and benzoic halide can undergo both of them, and we'll talk about how to make the distinctions a little bit later. So pause the video here, try to do these problems and try to understand why we're getting the products we're getting and why we're not getting particular products. Okay, competition between E1 and E2 reactions. So substrates. Primary and secondary alkyl halides will go through E2 reactions. Tertiary alkyl halides, E1 and E2 reactions. Primary, secondary, tertiary, allylic, and benzoic halides, E1 and E2. So this kind of sucks, right? There's only really like one distinction we can make to be sure that we have an E2 reaction, and everything that really goes through E1 kind of goes through E2. So the way we favor one of them is we look at the base/nucleophile. So stronger base, recall that in E2, this reaction rate is based on the alkyl halide and the base. E1 only cares about the alkyl halide. So the stronger the base and the greater the concentration of the base, the overall faster this part of the reaction will be, the E2, versus this one, it will not. So low concentration of weak base will also favor elimination 1 reactions. Okay, cool. Stereoselectivity of elimination reactions. E1 and E2 reactions are stereoselective. E2 is a concerted mechanism, right? Because two rate entering steps, it all happens together. We need a very specific stereoisomeric relationship between the hydrogen that we're eliminating in our leaving group for E2. The beta hydrogen has to be something called anti-periplanar, which is just parallel and anti. So let's look at this, right? If we can draw a Newman projection to see this, H and X you can see are 180 degrees apart. Anti, therefore we can go through E2. These are right on top of each other, so we cannot go through E2. If these were next to each other, you could also not go through E2. The whole point of anti-periplanar is just because it avoids unfavorable electron repulsion between the leaving group and the base, right? Because as this leaving group leaves, it's negatively charged, right? And if we're using E2, we have a strong base, so we can kind of assume it's negatively charged. And negatives and negatives do not go well together, right? So we need to keep them as far away as possible. It's kind of the same general principles that you learned when you took Gen Chem and learned about Vesper theory and like all of the 3D orientation theories. Okay, don't worry too much about anti-bonding, bonding orbitals. Okay. Consequences of the anti-parallel requirement. If the alkyl halide has two hydrogens on the beta carbon, we'll have E and Z. E will be more stable because we have, a greater distance between the big stuff. Z will not be as favorable, but it'll still be formed. Okay. And sometimes to see the E and Z, we have to do rotations, because recall that free bonds have rotation, like free rotation. If there are two hydrogens on the beta carbon, both the E and Z alkene are formed, and the major product is based on sterics, right? So it's generally E. If the alkyl halide only has one hydrogen on the beta carbon, first of all, only one product will be formed, and it won't always be E, it won't always be Z. It'll be based on where the Br is and where the H is, and if we are able to make them anti-periplanar. Elimination with cyclic substrates. So this is really important. Both the groups, the hydrogen and the leaving group, have to be axial, okay? This is up, this is down, it's axial specifically. This is down, this is up, it's equatorial, it does not work.